There's been some questions on the FEMAP group on Yahoo recently regarding linear versus nonlinear buckling. I'm going to use this sample model of this simple tower structure. It's basically 6061 T6 aluminum, 6x6 tubes as shown there, and also 4x4 cross stiffeners. We usually use this model just as an introduction to FEMAP and FEA modeling. You could certainly just TET mesh this entire structure and use glued contact and NX Nastran to hook all this thing together. However, the model is going to be quite large. You can see there that mesh-wise, it's 1.8 million nodes. In a linear static type situation with some of the new iterative solvers, you could certainly run a statics run on that in a reasonable time. However, as you go a little deeper into analysis, like we're going to do today, with a nonlinear buckling, and you get into a transient dynamic solution, the model solve times are going to get to the point where it's basically prohibitive, especially for making changes. So what we're going to do here is basically the standard process a FEMAP user would use. You bring in your solid model, extract some center lines to find the center of the geometry, and then the analyst would basically specify a material property, our 6061 T6 aluminum. You then set up your cross sections, the simple 6x6, 4x4 boxes, set a global mesh size, and then mesh it. So we can make a model very quickly. It's a very limited number of nodes. You can very quickly edit the material properties and/or the cross section properties and change the thicknesses of the tubes. And you can also very easily add or remove stiffening tubes to kind of optimize your design. So it's kind of the point of idealizing the structure as shown. But today we're going to look at setting up the model for linear buckling versus non-linear buckling. All right, here's our model as you saw in the introduction there, but just to give you an idea, it's got the cross sections turned on, but it's basically just a simple beam model. We've got a vertical or a downward force at the 4 corner nodes, and the bottom is constrained at the bottom there. So fairly simple model. So let's go ahead and set up a linear buckling analysis first. So I'll go over to the model info pane FEMAP and say manage, and I want to create a new analysis set here. So I want to do a buckling, and I can give it a title, make that linear buckling, say OK. And we could go here and set a bunch of options, but FEMAP actually by default sets you up straight away for a linear buckling. It's got our constraint set and our load set. There's really not a lot to do here except press the button and let an analysis run. And the model is very small. It's only 460 nodes, so it's going to knock it out pretty quick. It's already done pretty much solving. The results are already back in. So we'll go back and let's just take a look at what we got here. So it does a static load case and then the buckling case. So eigenvalue at 0.7999. So basically at 80% of the load applied, this structure would buckle. So I'll right click on that results and say deformed. And actually the undeformed model is also displayed. So I guess the geometry is being displayed. Let me turn that off. Geometry's off, and there's the blue is the undeformed structure. We can turn that on and off with this flag here. But you see the deformed structure, so the tower buckles at that 80% load, and that is basically done with a linear eigenvalue analysis. Now the question has been, how do we do a nonlinear analysis? Basically in FEMAP you need to create a function to ramp the load up. So I've already created this function, but I'll just show it to you. We'll edit it. You'll see it basically just runs from at time 0, the factor on the load is 0, from time equals 1 to the factor on the load to be full 1 times the load, so basically at 100%. So then we can set up our nonlinear analyses to basically use this ramping up of the load. So back on the load itself, we're in load set 2. There's a load definition, force on node. If I edit that load, you'll see that function has been attached to my loading, basically making it a ramped up nonlinear load. So just like we set up the linear buckling run, we're going to go into our analysis manager, say manage, and I'm going to create a new analysis set. And this one, instead of linear buckling, I'm going to go down and go to a nonlinear static run. Now this basically will ramp it up statically. It doesn't take into account any motion and inertias and things. We'll do this first and say OK. And again, FEMAP does set up the defaults. It does have the boundary conditions already in. Those loads are in. But I do need to set up some nonlinear options. I'm going to hit the defaults button, let it fill in the defaults. Let's do 10 time steps. We'll say max iterations per step at 25. And I do want intermediate output. That way I'll get the results in between, so we can kind of do a nice animation of it ramping up. So at this point, that's really all I need to set up. I'm just going to make sure that set 2 is the active one, and then hit the analyze button again. Now this is running a nonlinear run, so it's actually got to do a little more work, but the model is still pretty small, so it's already through a lot of iterations. You also get load step conversions. And I think what happens here is it basically fails to converge once it gets to the buckling load. So we'll go ahead and read in those load steps, and we'll see that basically it starts iterating in, not a big deal in the linear region here, but it gets to the point where the model goes nonlinear, and that's when it basically fails to converge after that. So I'm going to use the shift key to pick all these result sets, and I can say do a multi-set animate, and we'll see actually, you can actually see the linear portion as it's still linear, and then it starts to go nonlinear. So it's kind of the difference between the linear buckling and the buckling and the nonlinear buckling. And you can see it starts to happen right about the same point, but there is certainly the point after buckling where the thing is still carrying load. It's just displacing a lot more until it gets to a major failure when it fully buckles around this 84% of load. So the true failure or catastrophic buckling would happen a little bit higher than the linear analysis shows you. Just to give you an idea of this a little bit more, let's go into an XY plot. Node 129 is one of those corner nodes up there, and I can say, I'm just going to pull, we need a Z translation. So that's T3, and I can say, show me from those load sets a plot of that nodal displacement. And you can see what happens here is that everything is linear up to a certain point around 80%, which is where the linear buckling tells you things go wrong. But then you really don't get to a major change in displacement until a little bit higher. So if I turn on the data points here, let's put on the pairs there, or I can put the values is good enough. Is that right? No, those are displacement. Let's put the full pair, data pair. So I could zoom in down here at end where it's starting to go, and you can see that at 82.5% of load, it's still fairly linear. At 82.8 is when it really starts to drop off. So that kind of gives you a better idea of the true buckling behavior of this part.